So for this one, obviously it's kind of hard to explain through words. So I think the easiest way would just be to show you. So share my screen for a sec. So if you look at the first one, so it's just one flow, so one directional flow, Vx is equal to By. Okay. So showing that, so we have this something like this, right? So Vx is equal to By. So what does this mean? So the first thing that we can say is that the velocity in the x direction is a function only dependent on y. So what does that mean? What it means is if we had a channel, so like something like this, that is a terrible channel. So something like this, right? So this is our channel. Okay. We had flow. So this is flow in the x direction. So if we set up our coordinate system, something like this, maybe we have x here, and then up top you have y. Then you would have some sort of flow like this, right? Saying that this flow is dependent on y. So if you think about the potential of a velocity profile, right, we'd expect W to be something like this right then, because this would be the only non-zero value of the velocity. When you do the when you apply shear, when you apply the stress tensor, this will be your non-zero velocity profile component. So, and obviously because this is a constant, this whole thing is a linear term. The velocity profile would look something like this, where obviously no slip here, so no flow, because we're assuming that this surface isn't moving at any velocity. And obviously smaller gets bigger. So what this means is that at different values of y, so depending on what the y input is, so if say this was like 0, say this was like the height you're measuring, and then it's like 1, and then 2, and then 3 here, the values of velocity will also vary from like 0 to the maximum, whatever that might be. So representing this now on an XY diagram is something like this. So here's our coordinate system. Now, for positive values of y, Vx would also be positive, right? So if y was equal to 3, Vx would equal to 3x. So what that means, looking more in depth to it, is that means that the velocity in the x direction has a positive value. So that must mean that if we label these as y here, so if you look at it, what that means is for positive values of y, which is all of this shaded region here, right? The velocity in the x direction is in the positive x direction because Vx is positive, right? It'd be like 3b or 2b or 1b, they're all positive values. So if I was to represent that on the xy diagram, it would be something like this, right? velocity in the positive x direction in the positive y region, going in the positive x direction, and at different values of y, because it's like here at different values of y, the magnitude of the velocity is different. And then same thing applies to here at the bottom, where the values of y are negative, then vx is negative. So therefore we are traveling in the negative x direction. And once again, different values of y, different magnitude or different scalar values of the vx term. So that is, if you look at what he shows, that's what we got here, right? It's just that I've extended it out a bit more, but yeah. The next one, 9b, I won't, I'll do 9c because they're quite similar, but 9c is a bit more complicated and it looks nicer because it's swirly. So 9c, we have vx is equal to minus this b, so minus by, and then by is equal to bx. Okay, so let's go and do that then. So vx is equal to minus by. So vx is equal to minus by, and then we also had v equal to bx as such. Okay, so same thing here for the y term, which I will show in red this time. If we're in the positive y region, entering in a positive value of y, vx is going to be negative. So what does that mean? That means that the velocity in the x direction will now be in the negative x direction, right? For positive values of y. So that means focusing on the upper sections, we have something like this, right? And obviously, you know, different magnitudes of these arrows, because the length of these arrows figuratively represent the magnitude of the size of the velocities. So, you know, different values of y, different magnitudes, but I'm only going to show two in this case. Same thing applies if y was a negative value, so looking in the bottom negative region, if we input a negative value of y in, this whole term will be positive. So what does that mean again? The velocity in the x direction is now, for negative values of y, is in the positive direction. As such. Now for this one, if we go back to our analysis before, we said we can rewrite this as v of I is a function only of x, right? So once again, what does that mean? That means, let's erase this. So if we had like a vertical channel, right? We had fluid flow in the y direction. I'm using this as the coordinate system here again. So we had fluid flow in the y direction as such. And what this is saying is that if you look at, once again, if you look at the stress component, our only non-zero value of the stress tensor would correspond to a velocity profile, or a non-zero velocity profile of only Vy. Can't say the word Vy. Dx, right? So once again, drawing the velocity profile, this is linear again, so it'd be maybe something like this, maybe. Yeah. So once again, these 2 points would be 0 because non-slip, and then you just have increasing values as such, depending upon what the values of x were. So if you imagine like the width, this would be like a 0, 1, 2, 3. So the magnitudes would change. So again, applying the same kind of logic or notion to this, if I use blue to represent this, for positive values of x, the y would be positive. What does that mean? That means that the velocity in the y direction is now in the positive y direction. We show this by going up, right? This is also the positive x region because all these numbers are positive. So same thing apply here. For negative values of x, Vy is negative. What does that mean? Velocity in the y direction is now in the negative y direction. So for these region in the left-hand side where x is negative, velocity will be pointing away from the positive y direction. Okay. But now you've got an interesting dynamic here because you've got flow now in one direction, and you also got flow here in another direction, right? So part of those flows will not interact and they'll just go their separate ways. But more often, modeling this to a more accurate situation, they'll combine, interact, and there'll be a resultant velocity component depending upon the direction. And the resultant always acts, if you draw it like this, it's always acting through the middle, right? There's a bisecting. I'd try and bold it, but you know what I mean. It's gonna be the resultant that acts through. It's gonna be the resultant because if you draw out the triangle in a different way, so here's the resultant here, here's this one across there, and then here's the one that goes down. You form a right angle triangle with the resultant being the hypotenuse. So if you did something similar to like force analysis or something like that, it's kind of the same thing applies here. So drawing the resultant now, we have flow going in this direction, flow going in this direction. So the resultant would be this way. This is flow going down, flow going across. Resultant would be this way. Flow going up, flow going across. Resultant this way. Flow going across. Flow resultant this way. And that's it. You've taken into account all the different variations in the flow profile. And if we compare this to what he's done, yeah, you can see that we made the nice swirly design, which is always good. And then, so you can apply the same kind of logic to 9b as well. And then looking at 9D, we have a profile, a Z profile as well of Bx. And obviously thinking about this, if you wanted to incorporate the VZ, there's like a 3D plot, and ain't nobody got time for that. So pretty much the way that he's done it is he's just said that we're only going to focus on the XY plane. So let this equal to 0, as in say there was a value, so probably like x is equal to 0 here. So this is equal to 0. So it's like essentially saying we're only focus on the XY plane, which is good. This would be a pain to draw. You can have a go at drawing, I mean. So you'd have, okay. So x so considering only the positive directions of z, this is an x here. Using the pluses to denote which direction is positive and which is negative. Okay. Oh, as well, for 9D, it's a minus sign here as well, I think. Yeah. Okay, so I just scroll up this bit so we don't need it. So looking at the x component velocity, for positive values of y, this would be in the negative x direction. So that would mean we would have focusing just on like the xy plane because this is only a function of y. So it's probably, you imagine this flat on. Now switching to blue. For positive values of x, this is because the minus sign. This now means that the velocity in the right direction for positive values of x will be in the negative y direction. So again, this will be flat on the xy, something like this. And then now if we were to actually consider this one, show up, sort of orange. So for positive values of x, this would go up in, this will be positive, right? So this is velocity in the z direction for positive values of x. This will be in the positive z direction. Because that is only a function of y, we only have to consider the zy plane, right? Similar to here, x was only a function of y, so it only makes sense to consider flow only across in the y direction. Here we have z as a function of, I'll write out, so z as a function only dependent on x. So it makes sense to consider the y, it makes sense to consider the zx plane. So if you imagine the zx plane, which is this plane here, right, this rectangle, well, it's probably something like this if you imagine it's on the plane. And then combining the whole thing, So now you have a 3D combined. Oh yeah, I just showed the Z plane. I like this thing here. Now, combining all of these, which is always fun. You have one that's flat, the red one that's also flat, and then the third orange one that's going straight up, right? So you have to find the resultant of all three, which is probably, okay, I've drawn that horribly. I'll draw that again. Going like this, one going like this, and then one going straight up. So the resultant of all three, we would expect it to be already used red. It would be something like this, right? Because if you line up all of the things from hypotenuse, so it'd be somewhere along like this, maybe. But obviously, he didn't do that. He cheated and just focused on the XY plane. But yeah. And then you'd also have to consider the components on each of the separate ones as well, because now you would have this component here, these two forming one. So these two might also form what we saw before, because we have one going like this, one going like this. So resulting in the XY plane. Yeah. And essentially, when you do the whole thing, you have vector field of all the different flows in all three directions. But obviously, he didn't want to go that far because he's lazy. But yeah, that's it.